In this video, what I would like for us to do is set up and use the second order Taylor polynomial, what I call T sub 2, in order to approximate this scalar valued function of two variables, which is being given to us as f of x and y is 1 over x squared plus y squared plus 1. Okay, I'm going to do this two different ways. The first way, which we are going to do right now, is to just use what we've been discussing about Taylor polynomials to write down T sub 2, and then we will plug into it. Okay, so what do I need for T sub 2? I need to evaluate the function at some kind of center point, and then I need to do the gradient and the Hessian at the same center. What center should we use? Well, if you look at what we're trying to estimate here, you have to think like, is there some point in the domain near this point where I can easily evaluate my function? Now, we will allow ourselves to use a computational aid at the end, but the idea is that, like, of course, if you had a great calculator, you wouldn't do any of this. You would just plug into it. So you have to imagine, like, well, what if I didn't have a great calculator and all I had was pencil and paper? What would I want to compute instead? And what you would want to compute instead is f at 0, 0. Because at the origin, we have 1 over 1. Okay, so it's 1. F of 0, 0 is 1. In fact, we need that for the Taylor polynomial. So let me go ahead and write that down. The origin will be the center where we compute our Taylor polynomial, and then we will plug in near it by plugging in 0.2 and negative 0.3. To save space, let me move to the right. Let's do the gradient of f at 0, 0. What I'm going to do is evaluate this and plug in two steps. Okay, so we have low d high minus high d low, so minus 2x over low low. By symmetry, the second one will be negative 2y over x squared plus y squared plus 1. And we're evaluating this general gradient expression at the origin, which is just going to be 0, 0. Okay. Next up is the Hessian. For that, we need to work with this expression. Take a moment to go ahead and do that first on your own, and then I will come back and show you how I would work through the Hessian. Then we will set up the Taylor polynomial we need. All right, I wanted you to do that on your own because I'm going to be much more direct about plugging in x equals 0, y equals 0 as I write this. Let me pull the negative 2 in front. And then what we expect to have is a 2 by 2 symmetric matrix where the first column will look like the x and y partial derivatives of this expression, and the second column will be the x and y partial derivatives of this expression. Okay, I've pulled the negative 2 out front, and what I'm going to do is compute these and keep in mind how the quantities behave at 0, 0. So let's see, for the first one, it's low d high, so that's going to be 1 times 1, minus high d low, but when I plug 0 in for this, it's going to wipe everything out, over low low, but that's just 1 squared squared, so over 1. And then likewise here for this coordinate, if you wanted to, you could say that's also 1, 0 over 1. And the reason for that is the symmetry of these two computations. So differentiating this with respect to x looks a lot like differentiating this with respect to y. Now, if I differentiate this with respect to y, low d high is 0, minus high d low is minus 0 times something, so this is going to be 0 and 0. Okay, I did that kind of fast, but again, I hope that you went through the computation with as much depth as you needed before I came back and did this for you. So overall, this is negative 2, 0, 0, negative 2. Okay, let's write down the second order Taylor polynomial now, centered at the origin. It's a polynomial expression in x and y, and it looks like this, plus the gradient, which I will go ahead and write just for completion. So that gradient, oh, sorry, this should be plus, and then I'm going to write a dot product. Okay, so 0th order term plus the gradient dot the difference vector x, y minus 0, 0, or coordinates x minus 0, y minus 0, plus the second order term, which as this is a little bit more new, I'm going to do it in a different color. So let's do 1 over 2 factorial, x minus 0, y minus 0, transpose, negative 2, 0, 0, negative 2, x minus 0, y minus 0. Okay, I wrote a lot here that you don't need to write. like this dot product, which I knew was going to be 0 because one of the vectors is 0, and also all of these subtractions of 0 is kind of silly. Take a moment to just pause and make sure that you've got the same second-order Taylor polynomial. When I come back in a second, I will show you how to do this triple product very quickly so that I can write the entire polynomial right here in the bottom right corner. Then we will use it to estimate the value of our function at 0.2, negative 0.3. Okay, let me write this Taylor polynomial down here, actually. So we have 1 plus 0 plus 1 over 2 factorial times this matrix triple product. Now there's a very fast way to multiply this row times this 2 by 2 matrix times this column. And before I tell you that, let me just recognize first that we will get 4 types of variable combinations from this matrix triple product: x squared, y squared, xy, and yx. Of course, we will mix, or we will add the xy and yx components together. So how can you get x squared? This term will meet this term together with this entry in the matrix. So that negative 2 in the first entry in the first row matches with the first entry in the first entry. Similarly, y meets y, giving us y squared with this bottom right corner. And then we have x meets y. This pairing goes with this 0 in the top right corner, and y meets x with this 0 in the bottom left corner. So in fact, we won't add those terms together because they're both 0. But overall, you can say, all right, it's x squared times this, y squared times that, xy times twice one of these off-diagonal things. So it's a very fast triple product to do. Ultimately, looking at this, we're going to have, just from this triple product, negative 2x squared minus 2y squared, but then we're going to divide by 2 factorial, leaving us with minus x squared minus y squared. Okay, so that is the second-order Taylor polynomial approximating this function. If we wanted to estimate the value of this function at x equals 0.2, y equals negative 0.3, if you plug into f, which you're welcome to do because you probably have a calculator handy, you get approximately 0.885. If you plug x is 0.2, y is negative 0.3 into the second-order Taylor polynomial, you get 0.87. I think that's exact. So 0.87 versus 0.885, they're reasonably close together. If you took this input and moved it even closer to the origin, you had x is 0.02, y is negative 0.03, they will probably agree more significantly. Okay, at this point, we could be done with this exercise, but I would like to come back and revisit how to get to this Taylor polynomial using a bit of a trick. You might look at this polynomial and look at the denominator we started with and say, hey, that seems like something is going on in the background, and let me just quickly explain to you like another way that you could approach this problem. That connection you may have spotted between the denominator of the function that we started with and the form of the second-order Taylor polynomial that we wrote down is actually because we could have reproduced that polynomial if we recognized that a very, very famous series for functions of one variable was actually applicable for this function of two variables. So in particular, recall this series kind of built off of the geometric series where you have 1 plus u squared plus u cubed, et cetera, et cetera. If the absolute value of u is less than 1, then this series converges, and it converges to this function 1 over 1 minus u. So we have a function that could be put in that form. Let me take 1 over x squared plus y squared plus 1 and write this as 1 over, I want to keep that leading 1, but then I would like to have minus something. So how about minus negative x squared minus y squared? Okay, now this is in the right form where u, this expression u, is like minus x squared minus y squared. This will converge for us if we are within the unit disk. Well, our goal was to be near 0, so that's fine. If I start to expand this, we get 1 plus u is now going to be minus x squared minus y squared. And then plus u squared would be plus minus x squared minus y squared squared, et cetera, et cetera. Now, this expression here corresponds to the first order term for u, but u is actually quadratic in x and y. So that's why this is t2 of x and y when we go back to the original variables. Okay, so I just wanted to connect what we were able to compute without thinking about this on a few minutes ago to something that you may have learned in single variable calculus or real analysis 1. Okay, thank you for your attention.